Yes, so the title of my talk here today is Geophysics in a Changing Climate. And we're going to look at this from a few different angles, both with respect to the climate change emergency that we are in, as well as the social aspects and the dynamics that are really we're observing as our field is actually changing and the way we interact and we solve problems is changing. And so I want to start by acknowledging where we live and work in Vancouver is located on the ancestral, traditional, and unceded territory of the Musqueam, Tsleil-Waututh, and Squamish nations. And I think that it's important to acknowledge both the physical space that we're in and the social landscape that we're in, and those will be themes throughout. So as I mentioned, one of the first things we'll be talking about is the climate crisis. And I've got just a selection of images and topics here where geophysics, I think, has a really important role to play. So critical minerals and mineral exploration is something that we all very much have in common in this room. Aspects of CO2 sequestration. So there's two avenues I'll talk about there, both with respect to sedimentary settings, but there's some really exciting work looking at carbon mineralization. So an intersection with the minerals industry and sequestering CO2. Then also things where we're looking at understanding and mitigating impacts of climate change. So monitoring permafrost and projects, particularly in Canada's north, understanding and helping build infrastructure for certain communities. This is going to be changing quite a bit. And then groundwater is an ever-pressing problem and is going to be increasingly more so. Looking at places, both developing nations where groundwater is an important resource, but also first world nations. I mean, we look at California and it's a huge and very concerning problem to understand where groundwater is and how to appropriately manage that. And so these are all questions where we can contribute to understanding the subsurface and helping image and monitor. So let's take a look at each of these. So as Nihao mentioned, some of the BCGS talks have covered the topic of critical minerals, and I very much appreciated Alan Jones's talk in this series about the importance of mining and really the pressures that are going to be on the mining industry to find resources to transition away from a hydrocarbon-based economy. This was another interesting figure that I found. I know that the text is probably a little small to see here. But on what they're basically showing is year on year. So that first year is 1900 to 1909. And here is 2010 to 2019. And different technologies that are leading to discoveries and development, both on the project scale at the top and the prospect scale on the bottom. And the red color here is geophysics. This is within Canada. And you can see geophysics. And then this kind of orange one is geophysics and geochemistry. And so geophysics is playing, we're looking at close to 50% at the prospect scale. There's a really important and growing role. This is in Canada. Australia has similar numbers. So this is coming from the Minex Consulting Group. Australia has similar numbers, but worldwide, the role of geophysics is smaller than this. So Canada and Australia are kind of really leading the way. So that's perhaps an opportunity for growth. As I mentioned, so geologic storage of CO2. So we've heard a fair bit, and often with respect to connections in the oil and gas industry in sedimentary settings. So injecting CO2 or supercritical CO2 into saline aquifers or depleted reservoirs. But the other technology that I'm quite excited to see, and there's some exciting work happening at UBC, and this is work that we're getting involved in as well, is with respect to carbon mineralization. And so in certain mafic or ultramafic units, there are minerals that will react with CO2. And so this is looking at ultramafic units. And so this is some work that's been done by Jamie Cutts and Diane Mitchinson, so the UBC MDRU group and BRIM and others, the Geologic Survey of Canada. And so if we start off with fresh ultramafic rocks, if they are altered and serpentinized, so this first reaction is serpentinization, produces a series of minerals that can actually react with CO2. And one that's particularly important is called brucite. It reacts almost in real time. at surface pressures and temperatures. And so if this is a part of mines tailings or something, or rocks that we can bring up near to the surface, this is a really exciting potential avenue for carbon capture and storage, just taking CO2 and actually turning it into minerals. And so worldwide, there's a ton of potential here, but it is a very new technology. And then we're talking about managing impacts, so permafrost and groundwater. You're starting to really look at getting a lot more perhaps out of EM data and perhaps looking at IP. So really kind of drilling into these signals and seeing what we can get out, as well as the monitoring problems. So understanding time lapse and being able to characterize what's changing when we're talking about flow and making use of groundwater resources. So this brings to light a handful of, I think, really exciting and interesting research opportunities. So as I mentioned, questions in electromagnetics, we now have a lot of numerical modeling tools. We can simulate Maxwell's equations in 3D, but really getting the maximum we can out of those data. The perennial problem of integrating geology, physical properties, and geophysics is something that I think comes up over and over again, and we still have, there's still room for progress, and I think some really exciting progress. And especially now that we have, advanced inversion tools, as well as the growth of machine learning, I think really provides some really exciting opportunities to make some concrete progress in that problem. So let's take a look at each of these. So some of the challenges in electromagnetics. So some of the things I'm quite interested to be looking into, the impacts of permeability in EM. So when we have magnetic materials. So Alini Mello and Yago Ali have done some interesting work looking at on-time EM to try and get at magnetic permeability. With respect to highly conductive targets and looking at different scales, we've done some work looking at imaging when in their settings when they're steel-cased wells. So highly conductive, they're also magnetic. And what's quite interesting, so this is a small model, I know that's a bit hard to see, but we got a resistive background, it's 100 ohm meters, a casing that is a kilometer long, and a conductive target, it's 10 ohm meters. And so what's quite interesting is actually, if we look at this small target at depth, that's something, if we didn't have that well there, we simply wouldn't see it. But because we have this conductive well that channels current to depth, that actually makes it quite detectable. But then the question is, how do we work with these data? Because we actually need to be able to simulate the well if we want to actually invert these data. So that's with DC, but then if we actually go to EM, now we also then have to contend with magnetic permeability. So these plots on the left show, so at the top, we're looking at 3 different locations where we've run a time domain EM experiment looking for this target. The solid lines are with the target, the dashed lines are the background response without the target. And 3 different locations along lines, so 300 meters away from the well, 500 and 700 is the green. And so here we've got a conductive only steel case well. And so we can see, with above, so going beyond DC resistivity, we actually get a fair bit of very useful signal from EM. In particular, so here we're looking at the difference, and this is the difference as a percentage. So we have a very strong signal to noise ratio when we look at EM. If we then make the well permeable, there's actually a pretty significant difference. So these plots here are all now if we have a permeable well. And so first, just comparing these two, you see it's going to be quite important that we be able to simulate this and actually work with it. So that makes the physics more complicated, but the potential benefit is you can see that we have much larger signal over a much longer time. So it could potentially be advantageous if we can actually be able to accurately simulate this and estimate it in the field when we don't necessarily know what the properties of the well are. Some other interesting problems with respect to electromagnetics is really starting to go large scale. They are, yes, a complex system of equations to solve, but we have the computational resources to do that. And some of the problems where I think there's a lot of opportunity for advancement is looking at remnant magnetization. So Dom led a lot of really exciting work in his thesis looking at being able to invert for the vector. And to be able to do that in spherical coordinates and then apply sparse or compact norms so we can get back structures that look much more geologic. But really kind of scaling that up, it's a complicated inverse problem. And so there's work to be done to be able to make that simpler and be able to scale up. As well as looking at natural source EM methods. So seeing deeper is a problem that comes up over and over again as we're talking about finding new mineral deposits. And so natural source methods have a lot of potential there. But when we sort of look at literature and advancements that have been made in algorithms, I think there's room for development and some work there. And so I'm really excited by work that's being led by the SimPEG team. So in particular, John Cutai, Devin Cowan, Joe Capriotti, and Dom Fournier have been working on different aspects of this problem, from doing mesh decomposition, so using multiple meshes so we can scale up and solve larger problems, working on octree meshes. And so this is an avenue that I'm quite excited that we're continuing to make some progress in. Okay, and then coming to the big challenge of integrating geology, physical properties, and geophysics. And there's a fair bit of literature out there on this. And so starting perhaps with post-inversion classification. So I've got quite a few different images here. So on the bottom left is some work again by Alini and Yagua, the group at Colorado School of Mines. So looking at running independent inversions and then actually looking at the cross plots of the physical properties that come out and using that to then identify what the given rock units are. So building basically a quasi-geologic model from the geophysics. In the center here, this is from Jaja Sun's group at University of Houston. So they're actually looking at doing joint inversions and using, in this example was cross gradient. And so again, looking at the physical properties that are recovered and actually trying to really tie that to the geology. And then work that was led by the UBC group, looking at the Talik Waicho kimberlite deposit. And so looking at a suite of airborne EM or airborne methods. So looking at magnetics, gravity and electromagnetics, and also looking at IP from electromagnetics, and building up a rock model strictly from geophysics. And so being able to see what we can compare as we obtain from drilling with what can be achieved with geophysics. And that started by inverting these independently and then making some interpretation based on what we know of the physical properties. Moving forward, I'm really excited by the work that Thibaut Astic has really laid the groundwork for, of actually tying physical property information and a geologic characterization into the inverse problem. So really computationally tying these all together. And so you can see the picture of the PGI framework here. And so it's really three interlocking inverse problems. So we've got the kind of our standard geophysical inversion where we want to fit and respect our geophysical data. But there's a couple extra pieces that come in there where we're now actually doing a petrophysical characterization. And so this is going to start to promote clusters around where we perhaps know what physical properties we're expecting. And then using that to make a geologic identification. So having the algorithm actually build up a quasi-geology model. And so what I'm showing in these bottom plots is actually some physical properties with respect to the carbon mineralization problem. So we're looking at ultramafic rocks as they're altered. So this LOI is loss on ignition. It's basically a proxy for alteration. And so we start out on this side at 0 with fresh ultramafic rocks. This plot on the left is of density. And so as the rocks are altered, we can see that there is a decrease in density till we get to this inflection point, which is about an LOI of approximately 13. And this is kind of the sweet spot. This is actually where we've got brucite, we've got minerals that are ready to react with CO2. And then as those are carbonated, so reacting with CO2, the density again starts to increase. So in this case, density is a diagnostic physical property. Susceptibility is also somewhat, there's a much larger spread, but you can see sort of broadly speaking, rocks that have been serpentinized but not yet carbonated tend to have a higher magnetic susceptibility. And so if we cross-plot those, we're basically looking for this region where we've got a low density and a high magnetic susceptibility. So we've got this information about the problem and the physical properties that we're looking for. And so then the question is how do we actually go about and use this? So let's take an example. So this is motivated by the Dakar site in BC. So this was a site that's been studied in the MDRE report that was led by Diane Mitchinson. So what we have in the center is we've got, there's basically 3 blocks. Is we've got in green, a serpentinized block, and then within that there's a region that's been carbonated. And so we simulate magnetic data and gravity data over that using the values here. So the background is not susceptible. The serpentinized rock has a susceptibility of 0.15, and the carbonated rock is less susceptible at 0.05. And then the density, so the background we've got is 2.9. Serpentinized rock is less than that at 2.7, and the carbonated is more at 3.0. So these are the physical properties we're working with. We've got 2 simulated data sets. Let's go ahead and invert those in sort of the standard way that we would. So we've ran 2 different inversions. So on the left, we've got the susceptibility model recovered by inverting the magnetics data. On the top, we use the standard L2 norm that you see in most inversions. On the bottom, we've actually used and made use of these sparse and compact norms. So the L0 is what we applied to the smallness term, and the 1 is what we applied to the smoothness. And so you can see we get back a bit more sort of compact structures from that and kind of have less artifacts of it in the padding. And then what we've got here is actually histograms of the recovered physical properties. And so you can see there's a pretty kind of big spread, smooth variations. If you were just recovered this without necessarily knowing what the physical properties are, and you want to try and choose a threshold, what are we going to associate with the serpentinized rock? You'd be pretty hard pressed to choose anything. And in fact, actually, if you chose the true susceptibility of serpentinized rock for this L01 inversion, we wouldn't recover anything. Because the inversion, we smooth things out, we're not actually going to be able to recover those true physical properties. And you can see the same thing happening with the gravity inversion. But let's see what we can get out of this. So if we have these recovered inversion results and we want to build up a quasi-geologic model, what do we do? So what we decided to do is let's make a proxy model. So let's start with a model that we know. So let's just put a block in a half space. And what we'll do is we'll use the exact same mesh, exact same inversion setup as our data in the previous example. But now, because this is a synthetic example that we have control over, we know what the physical properties are. So we put in the physical properties of the serpentinized rock. So in this case, we're looking at the gravity. And so it was a density of 2.7. So we put a block in, we run the simulations, we run 2 inversions. And then what we can see is we can actually then go ahead and plot up basically what's the recovered volume as a function of the physical property threshold that we choose. So the blue here is the L2. And so you can see, you know, as if we pick the value of 2.7, we're not going to recover anything. But here, if we actually pick, for example, for the L2, if we picked a density threshold of 2.83, that would actually then give us the correct volume. And then for the L01, we can play the same game. And here we get a density of 2.79, and that would give us the correct volume. So with this, what this sort of proxy model is letting us do is say, okay, we know what the physical properties are, but through the inversion, we're not going to get that back. So we can then translate it to something that is perhaps meaningful with the inverted results. So let's go ahead and apply these and see what we get out for the recovered volumes of serpentinized rock. So the thresholds that we picked for the proxy is 2.83 for the L2. The true value, so because we knew the answer, this is synthetic, what we should have picked is 2.84. So that's actually reasonably close. And then similarly for the L01, we picked 2.79 for our proxy model. And what it should have been is 2.81. So again, we're in the right range. And here we're getting back the volume of 27 kilometers cubed, which is less than what it should be. Here we're at about 35 kilometers cubed. But still, we're in the right range. By making use of physical property information, we can get out a decent estimate of how much serpentinized rock we have there. But this is all kind of post-inversion, right? As we've done the inversion, we've recovered these physical properties. What happens if we now actually try to bring this physical property information into the inversion? Oh, sorry. I was going to give you a summary slide first. So we did the same game for both the magnetics and the gravity, and this is just a bit of summary of both. And so you can see using both, with the magnetics, we got a bit of an overestimate. The gravity was a bit of an underestimate, but still giving us something that is somewhat comparable and representative of what's in the subsurface. But in general, we don't just want the volume of rock, we also want the structures, right? And so looking here, if we compare a few different models, the density models is bringing structure right to the surface, and we're seeing a fair bit of smearing at depth. Whereas the susceptibility models, there's maybe a little bit at the surface, we're not entirely sure. So let's also see what we can perhaps do to improve these recovered models and try and get something consistent between both by bringing in this physical property information. And so this is where we're going to make use of the PGI framework. And so what this does is we bring in the physical property information through a Gaussian mixture model. And so we define basically the center is going to be the mean. So for serpentinized rock, we see that the density is at 2.7 and the susceptibility is 0.15. And then we define variances or covariances around that. And similarly for the carbonated and for the background. And so this is then actually information that we're also going to try and fit in the inversion. So this is kind of come in actually as something that is going to be a misfit term, and we want to respect these data in the inversion. And so in this example, we ran, and here I'm just showing you the joint inversion results. You can also go and treat each of these independently. But here we ran a joint inversion. And so what that is then going to try and do is fit the physical property information. And then using that physical property information, we actually build up a quasi-geologic model like through the inversion process. So this isn't something where we needed to go and pick thresholds. The quasi-geology model is built as a part of the inversion process because we're including this physical property information. And so benefits, I mean, we get one model that's consistent with both. We don't have to try and reconcile these two different models. We've improved the estimate of the depth of the serpentinized units. We don't kind of have that smearing up to the surface. And then the estimates that we get out. So if we look here at the serpentinized rock, it's, I know that's small, but it's about 58 kilometers cubed. So it's a bit larger than what we expected because we perhaps see some of the smearing at depth. But a really important thing, you know, the total volume is one thing that's of interest, but also of practical interest is the depth. And depth within certain ranges. So what's near the surface, what is too deep to be useful. And so here what we've plotted is the cumulative volume as a function of depth. So the gray dashed line is the true result. And then the blue is the L2, the orange is the L01, and the red is the joint PGI. And so on this side is from the magnetics data, so the susceptibility, and then here is from the gravity inversion, so with density. And so let's, for example, if you look with this one, you can see basically that it's pushing, the L2 is pushing structures deeper. Here it's actually bringing structures shallower, whereas the PGI, by including both physical properties, we're doing a really good job actually recovering where structure or where material is with depth. And it's consistent between both physical properties. So this gives you a bit of a sampling of some research avenues that I think, you know, in geophysics, we have some exciting and really interesting work to be doing. So as I mentioned, questions in electromagnetics. So when we have strong conductors or magnetic objects or chargeable objects, how do we tease all of this apart and really make use of those data? There's a lot, I think, that could still be advanced with integrating geology, physical properties, and geophysics in joint inversions. And the PGI framework, I think, gives us a really nice foundation to build upon. And starting to look, for example, at using EM in there, where we now have a nonlinear inversion. So it is going to be more complex. Most of what I just showed you is potential fields, which is a bit of an easier problem. Similarly, if we have remnants, then we actually have multiple properties that we're getting from a single data set. And then also the role of machine learning. So the PGI framework uses some classical methods. So a GMM is kind of a classical method in machine learning. But there's algorithms and so much work being done in that space and so much being developed for us to leverage. And so, we take a look again at these problems, and there's some really interesting scientific work to be done. But I think that it's important to also recognize the context that we're in, and how geophysics can contribute as a field to solving these problems. And so, took a look back. Let me see if I can move this because I wanted to show you. There we go. So took a look back at the Journal of Geophysics and the Society of Exploration Geophysics, sort of, being one of the largest bodies that represents applied geophysics. So the first geophysics journal, or the first articles, were published in 1936. And so it looked at just a random article in 1955. So let's go back and take a look at what sorts of articles are being published. And so grabbed all the titles and the authors, and you can see there's quite a mix, everything from magnetic delay line filtering, gravity inversions, EM. There is some work with respect to lots with seismic, wave propagation and stratified medium. And so if we take a look, and I'll gray out here the methods and the papers that were really tied to seismic or hydrocarbon exploration. Oops. And so you can see that there's a pretty good mix in this single issue that came out. It's about sort of half EM potential fields, other applications, and about half related to hydrocarbons. And so yes, there's a lot of the history of geophysics that's been in hydrocarbons, but seeing this is encouraging that there's some interesting work that was being done with respect to just fundamentally understanding the physics. And so let's fast forward a bit. Where are we today? So I did take a look at the article and the latest issue, and was going to put the titles out. One thing is we publish a lot more articles in a journal than we did then. It would not nicely fit on this slide. So a bit of overwhelming amount of information. But still, looking at the geophysics, at the Society of Exploration Geophysics website, the first thing you see is connecting the world of applied geophysics, so really representing applied geophysics. And you take a look, so I went to this page, what do geophysicists do? And quite frankly, I found this rather uninspiring, is that the first part of what they say that geophysics does is hydrocarbons. They say, that the world needs to transition off of hydrocarbons, but we still need to be finding hydrocarbons. And sure, there's some truth to that, but where's the vision in that? As folks students who are excited to come and make a positive impact in the world, doing some serious physics computation, being tied to a declining industry, a sunsetting industry is not necessarily an inspiring first impression. Another thing that stands out in here is mineral exploration is not even on the list. There's no word mining here, and so it's not sort of even in the context of what is moving forward. And that was pretty disheartening to see in the SEG, that mining is going to play an extremely important role in transitioning off of hydrocarbons, and we should be a part of that conversation. So this, I think, raises a few questions that I really hope prompt discussion. I'm not going to answer any of these, but I think that as a community, we should be chatting about these. So I think, one of these important questions, where does geophysics fit into interdisciplinary problems? We have a lot to offer in terms of imaging and characterizing the subsurface, but it is one piece of the puzzle and needs to actually be integrated with geology, be part of that conversation, bringing data between different disciplines. And that's a challenging thing to do. The question of who is involved, and I'll come back to each of these, and as well as this kind of alluding to the last slide we just looked at, is the brand of applied geophysics. How do we talk about what we do? How do we introduce it to students? So first, starting with interdisciplinary questions. I think, well, as we've talked a bit about, there's some really interesting and exciting technical work to be done, combining machine learning and inversion. So being able to respect the physics, being able to bring in both quantitative and qualitative data, we have now opportunities to start really seriously exploring that. And in order to do that, we really do need collaboration between disciplines. So both being able to actually send data back and forth and be able to understand, what each other are working with, but also with respect to language and how do we actually communicate and speak to each other about what information we need, what information that we can bring in. And so I think one important aspect here, and I think this has been really exciting to see the growth of open source software in the past few years. As a first step, being able to actually take a model from a geologist and being able to translate data formats and get that into geophysical inversion software is an important sort of first baseline. If there's friction there, that's a problem. And so projects like, for example, Subsurface is a project that's really working on actually making it easy to interoperate between different software packages. So that's quite exciting. I would put, and Dom's not in the room, but I wanted to put the GeoH5 Pi and the Geo apps on here as well, because I think they've been really important in making these software tools accessible. But he doesn't have logos for them yet, so we can bug him about that. Yes, but I think, so being able to translate data back and forth, but what I think is so exciting that so many of these tools now exist is being able to really look at how do we much more deeply integrate them, is being able to iterate more rapidly between a geologic model, geophysical model, and have that be much more fluid. So the question of who is involved. And I think that, we have been making progress on gender equity in geophysics. We still have room for growth there. But an extremely concerning pattern and observation that folks have had is the progress on racial diversity. And so this is a pretty striking title, No Progress in Diversity in 40 Years. That's more than my lifetime. And so if you look at actually all of the STEM fields, geosciences, they don't quite break it down to the subdisciplines, but the geosciences has the lowest proportion of racial diversity of all of the STEM fields. So one statement in this paper here was the bigger picture. So in 2016, only 6% of geoscience doctorates awarded to US citizens and permanent residents went to students from underrepresented minorities, which is a group who made up 31% of the US population that year. So that's a pretty striking statistic. And we have some work to do there. And similarly, so there's challenges here, and we're also even the enrollments are dropping off. And so this paper here says the US geoscience enrollments in degrees collapsed in 2019 to 2020. So some of that is probably COVID related, but this pattern here, for example, the drop off in undergrad, that year here is 2015. So it's not just COVID. We are actually seeing a drop off in enrollment, and we've seen geophysics programs being cut and reduced worldwide at this point. And so we're in this place where we've got, I think, some really exciting, interesting, and worthwhile, meaningful problems to be solving, but we're really having trouble attracting students and being representative of the population. The problems we're trying to solve impact everyone, and we need, if we're missing out on voices and ideas, then we're losing out on that. So what are some ways forward? So here are a few ideas, and as I said again, this is meant to prompt discussion, and this is by no means a complete list, nor should it be. But I think we need to seriously look at what is the branding of applied geophysics, and I think this is a really exciting opportunity for BCGS, for KEGS to step up, and we can share what our narrative, what we want that to be. So a couple of points that I put here, connecting with values. So what I mean by that is, the attraction and how students are choosing disciplines and what they choose to study in their degrees is no longer nearly as driven by, a job security, a well-paying job in the hydrocarbons industry. People want to be spending their time on problems that they care about. And I think we offer that, but we need to be able to tell that. And so being proactive on what we can be contributing to climate change solutions and understanding the impacts of climate change are things that I would hope as a community we can really talk about, and we can build a narrative in our story around. Also including an emphasis on technology and computation is, often being outdoors and being connected with the field is something that really, draws a lot of people to geoscience. But there are also a lot of people who are really excited about technology, computation, and want to see that applied to the environment. And so how do we really reach those folks who are really technology driven? Because we have a lot to benefit from them. And yes, as I mentioned, I think societies, BCGS, KEGS, and maybe SEG have an important role to play here in maintaining and promoting and telling the story of what applied geophysics is. Engaging with students. I've been so excited and inspired to see the scholarships and the internships that bring students into the fields and give them a place and tell them that they are welcome here. I think that's a wonderful thing. And then I've put some logos here on the right-hand side of a few initiatives that I think are making a positive impact. And I think another thing that we can do is, look out for groups like Women Geoscientists in Canada, GeoLatinas, Big Black in Geoscience, and do what we can to amplify their voices. If there's places that we don't know what we should be doing, but we see others who are doing a good job, finding out how we can support and amplify those voices, I think is a positive step. And there's ... and question marks. So I hope that all of us together can maybe fill in a few more ideas here. So with that, I want to say a very big thank you to the BCGS, everyone who's organized today, and all of you for coming and waking up early to spend some time together. So thank you.
We have time for some questions.
I've got a couple of comments, a technical question later. But first of all, a comment. The KEGS Foundation scholarships and the BCGS internship are open to non-Canadians. So if you know a student from wherever in the world, encourage them to apply. That's the only way we're going to improve this dismal racial inequity. Just to have more students come to Canada, learn geophysics, get jobs, so on. My other comment, on a light note, is I was really interested to see your slide of the paper from 1955, of the journal from 1955. When I was at Queen's, when I had a spare afternoon, I'd go down to the library and just yank out an issue of Geophysics at Random from the 40s and 50s and leaf through it and look at the papers that were there. It's really interesting to see the kind of work that people were doing back in the day. I still do a little bit of it, not as much. I don't have as much free time now. I'm no longer a professor, but that wasn't. I still have a complete collection of geophysics, right back to 36. Every single one I've got in my attic, in my house. And occasionally when I go, something tweaks my interest, I go back and start looking at an addition, but it's a fun thing to do. Now for the technical question. I noticed the lack of resistivity in your presentation. And it's another parameter. I mean, density and magnetics is important, but resistivity is important too. It's a little harder to collect resistivity data. You can't do it from the air. But that's, you have to bring that in as well. And I'm sure you're doing that. Maybe you could tell us a little bit about how you're bringing resistivity in so that it's not just 2 parameters, but 3 parameters to joint inversions.
Yeah, I think that's a great question. And so, I mentioned some avenues in electromagnetics kind of isolated from the joint inversion side of things. And I think with respect to joint inversions, that's a really important next step. And the PGI framework, being able to actually work with either electromagnetics, DC. Thibault's done some work looking at 1D airborne electromagnetics as well as DC resistivity. Bringing those in are more challenging problems because it is now a nonlinear problem. So there's work to sort of go into the mathematics of that and actually having that converge. But I think that's absolutely an avenue to explore. And one of the things I'm hopeful for is that there might be actually some physical property measurements on electrical resistivity or conductivity in the carbon mineralization setting as well. In so many places, physical properties are available for density and magnetic susceptibility, but it's not as common to get quite as much data around resistivity. So hopefully that's something that can also move forward.
Actually, I'd like to challenge you on that. There's a huge database from the petroleum industry on resistivity logs through the carbonates, because they've been using that for years for doing first pass geological mapping, and that's been underutilized in most areas by the mining community. It can be quite valuable. And then the Athabasca Basin, there is a wealth of data on carbonate, mainly because of the Athabasca sandstone. Resistivity has been used there decades, not as much as it should be. And it's actually one of the few methods that will allow you to actually accurately target your uranium resource there. And you can separate out the clays from it if it's done right. So there's a lot out there.
Point well taken. And I think that brings up another really interesting problem of the scales, the challenge of scales, is because what you see in a log and what you measure on a sample is different than what we see on a larger scale. And that's a fascinating problem.
Yeah, your resistivity log will be your most detailed log that you're doing a teleview of some sort.
If I can just add a little bit to what Dennis said about PEG's Foundation. One of the scholarships that's been recently created is for Indigenous students. And we want to get that word out, and not just to universities, but to colleges as well, because a lot of the northern communities might have students sort of going to colleges. And so we want to open this up and get Indigenous students involved in the geosciences. So please, if you spread the word about that, because it's got to get the word out. It doesn't really go. It's a bit frustrating to go to the First Nations groups themselves and the leaders and things, because they don't really know what you're talking about. But I think if we get the word out to colleges, universities about it, Indigenous communities, try to generate and increase that diversity.
If anyone wants to flyer the scholarship, come see me. I've got a couple for distribution.
I just two comments. I'll put two of them together. The first one is that when you showed the slide about the geophysics journals in the 1950s, the word, the titles, the vocabulary, they're written for people who have already got university education in geophysics and earth sciences. So they're inaccessible to the population. I work with projects in Europe where universities, geological surveys, search parties get together to get millions of dollars, euros. The European Union, one of the things that every project wants to do is disseminate to schools, disseminate to non-geoscientists. So we will take airborne radiometrics, in Germany will take it to high school, or village that's just into mining. All the conversations are 14 minutes. It has to be, because that's how you know. Yeah, I've been in Canada for 2 years. I haven't seen anything like that. And the third thing, I'm a structural geologist, so I expect clients that the reason geophysics is to test hypotheses. I don't see enough conversations. The geophysics is the method of producing certainty. So maybe there's some thoughts there. I just don't see any of those conversations. Geophysics.
On a different topic, climate change. Then we started to learn on what affecting magnetic north pole is happening. The magnetic north pole is a loop of 1,500 kilometers in the last 20 years, moving like 50 kilometers a year. Matter of fact, I think Putin cut it now. Sending us inside.
It's got a strong accent.
Doesn't that affect the climate? Is there any studies that how that affects the climate?
There might well be, but that's not something that I'm familiar with.
Yeah, I can't find it. Matter of fact, it's the other way. I've seen a paper saying that climate change is what's making it dead. Somebody was doing it. Yeah, I don't know why that doesn't.
Sid, there's a speaker tomorrow. It's at GOT. Who it is, but they're talking about magnetic fields of Ganymede and Mercury. So you might tune into that and ask them about the magnetic field.
Hey, Lindsey.
Oh, sorry, Doug, we had a point and then.
Yeah, I just want to kind of come back to maybe tying in a couple of the things that have been said. So Lindsey was talking about this carbonation project, which I think is really exciting, and that's sort of at that new level where there is potential for perhaps storing a lot of CO2. Take some technology advancement, but I mean there's potential there. And within British Columbia, there have been few places that look like they have potential. The challenge, from the point of view of going one step forward in research, is that it would be great to have a site that had both gravity and magnetic states. Most of the places have magnetics, but do not have gravity. If we extended that and could potentially find a site that for which there was also some kind of EM, so resistivity EM work, it could be just like a wonderful test site to do a lot of research in this particular area. So, the people know about this. There might be money that's kind of coming down the pipeline to actually carry out a gravity survey, but this seems like a good room to find out what people might know about a site that would be really interesting.
Maybe ultimately.
Yeah.
Well, yeah, the question is trying to come up with names and to really kind of figure out what we haven't had very much success.
This gravity was gravity. 2 kilometers by stations, there's a lot of middle BCs where these complexes are. And then there's one local scale.
Yeah, so we have the quest data, right? That's not resolution that's required.
You have to look at it as like problems. Like definitely the alpha basin. You've got airborne gravity, you've got ground gravity, you've got resistivity, you've got EM, you've got all of those components.
That's the problem with
No, there is along the eastern margin and the basement. You can't rule it for that. It's got all those components, but whether it suits the suits it. Easiest thing to try to do is graphite. Hardest thing really.
Yeah, so I've got a question. It's kind of tangent from the main focus, but yet I recognize an opportunity to ask SME and yourself here. So you showed the slide with the UBC inversion results and SimPEG inversion results. And I was just wondering if you could speak to the differences that we see in the 2 results there.
Oh, sure. Where was that? Yes. Okay. So if I recall correctly, I'm pretty sure that the main reason that there are differences that we're seeing here is we ran the SimPEG inversion for more iterations than the UBC inversion. So the codes themselves are quite comparable. The UBC code right now is more computationally efficient. It's faster, but we're working on that in the SimPEG code. Yeah.
Actually, the current efforts are to do a lot of sort of cross checks between UBC codes and SimPEG, because the overall development, the thing we see is that we kind of effectively industrialize codes that are ready. And then starting maybe 5 years ago, started to get a open source resources. So gravity, the magnetics, they're on par or better than what UBC codes. Again, the next up is the BC resistivity, which has been and IP, which is working well. And there's another step forward here over the next 4 or 5 years or something, where we really look at the EM problem and all its complexity and diversity, and to try to really increase that functionality and get those out into the open source so that people can long-term goals.
Excellent. Well, there's no further questions.
Oh,
you want to join
there's
me again?
One more. Yes, absolutely.
Quick question around the volume of rock you need to absorb. What is that relationship between how much CO2 is absorbed by?
So that then starts to depend on how, I think the questions right now are more so around what minerals react much more quickly. So there's a few, if we look here, I know that's extremely small. There's a few different minerals that you can see. And here you can even see there's kind of 3 different reactions. And so olivine can react with CO2, for example. Brucite is among them the most reactive. So I don't know exact volumes, but if you look, there's a couple of great papers, the author Kellerman, and there's been a National Academies report out of the US that looks at different carbon capture technologies. And the thing that's really exciting about carbon mineralization is it's basically the potential is at least an order of magnitude, if not several orders of magnitude, much larger than sedimentary settings. So there's huge potential there, but it is, right now, the technology really only exists for ex situ, so bringing the minerals to the surface. But there's been 2 projects done in basalts, so in mafic units, that actually inject CO2 subsurface. Well, interestingly, there's actually, and this is all kind of still hypothesized, especially in ultramafic units, but potential for reaction-driven cracking is because as it reacts, you change the volumes. And so it's quite possible that the reaction, that you'll be able to kind of continue fracturing. But that's still kind of very kind of an open question about how can in situ really work at any scale.
Don't want to try again.
I think you're good.
I do think that's everything. So I'd like everyone to join me in really thanking Lindsey for a great talk this morning. That concludes our sort of formal part of the morning. More than welcome to stay around and chat. Drink whatever's left of the coffee.